In Lesson 38, we'll be learning more about derivatives. The first part of this lesson is on the equation of the tangent line. Now, way back in Lesson 22, we first talked about what a tangent line was, and we talked about there that that was the main focus of differential calculus, was finding a tangent to a function at a particular point. We know that to define a line, we have to have at least 2 points, but for a tangent line, we just assume that those 2 points are so close together that we can call them the same point. The slope that we can find of a tangent line at a particular point, that tells us the rate of change of a function. And that's why calculus was developed, was to help us in that quest for understanding instantaneous rates of change for a particular pattern. Now look at this problem here. I have if y equals x squared minus 3x plus 4, compute dy dx, and then I have that bar and a 4. What that means is find the slope at x equals 4. Get a numerical value for the derivative at x equals 4. So that means the slope of the tangent line at that particular point, right? So let's take the derivative here. We would just say y prime, I'll just use that notation, is equal to 2x minus 3, and then the derivative of a constant just equals 0. So there's our derivative, y prime equals 2x minus 3. Now I need to substitute in a 4. So I need to just say y prime of 4 basically is equal to 2 times 4 minus 3. That would be equal to 8 minus 3 is 5. So I get an actual numerical answer on that. That's the slope at x equals 4 for that particular function. Now to understand this a little bit more, let's graph this function that we have here. And we'd have to get that in standard form for a parabola, and let's just rewrite that. We don't have to do all the calculations. It would equal y equals x minus 1.5 squared plus 2.25. So let's graph that. And the vertex of this parabola would be at 1.5 comma 2.25, so about right there, and it's going to cross the y-axis at 4. If we look back at that original function when x equals 0, y equals 4, so we can put a dot right there, and we see that it's going to be curving up like that. We can do a symmetrical pattern on the other side there. Now, if we wanted to know the slope of that function at x equals 4 at this spot right here, well, we'd have to extend that function out a little bit more until we cross that, and we could go up and just draw a tangent line at that particular spot. If I just go straight up, hit the line right there, a tangent through that spot would look something like that. Why I'm drawing that is just to show you that that does have a pretty steep slope there at x equals 4, and my graph isn't perfect, but we can see that it's definitely a slope greater than 2 or 3 or so. So just making that sketch gives us confidence that yes, the slope at that particular point, the instantaneous rate of change, in other words, of that function is equal to 5. And see, that is one of the benefits of calculus. I mean, we could draw a really, really good graph, but that's very difficult to draw a tangent line, a line that just touches at one particular point on a function. It's really hard to draw that line and to estimate its slope. But using calculus, we can just use some mathematical relationships here and come up with the slope very quickly, a whole lot easier than it would be to graph it, draw the line, measure its slope. Let's do another problem on this one. Let's find the equation of that tangent line, which can be drawn to the graph of y equals 3e to the x at x equals 2. So on this one, we want to find the equation of a tangent line. So that means we're going to be finding y equals mx plus b. We can find the slope of this tangent line by taking the derivative of that function. So we'll have y prime is equal to, well, it's an exponential function, e to the x, so the derivative is the same as the function, 3e to the x. The slope at a particular point, in this case at x equals 2, we would just have m for the slope is equal to 3e squared. Now we can go ahead and use a calculator and get a decimal value for 3e squared. And if you have a TI-83 Plus graphing calculator, all you have to do is hit a 3, hit the multiplication symbol, then do second natural log, and you should get like a little e with a hat symbol. That means e to the power of, and a parenthesis. Put 2 in there, close the parenthesis off, hit enter, and you should get 22.167, or about 22.17. So we'll have y equals 22.17 times x plus b. We still need to solve for b. This line touches this function at x equals 2. So at x equals 2, y equals 3e squared, or 22.17. So we can just substitute that in for our point that is on this line. 22.17 equals 22.17 times 2 plus b. So b will equal minus 22.17, and our function, or our equation then, is going to be y equals 22.17x minus 22.17. That's the equation for that line. That tangent line to the graph of that function at the point x equals 2. We use the derivative to find the slope of that line. We use that point, that one point where it touches the line, to substitute in and solve for the y-intercept. Part B of this lesson is on higher order derivatives, and all that means is like taking a second derivative, a third derivative, and so on. And for example, if we had a function f of x, the first derivative, we could use notation like this and just say d f of x over dx. The second derivative could be written like this, d squared f of x over dx squared. The third derivative might be written d cubed f of x over dx cubed. Now the squared and the cubed, those don't really mean anything. That just means that we take the first derivative, then we take the derivative of that to get the second derivative, then we take the derivative of that to get the third derivative. You could have fourth, fifth, sixth derivatives, and so on. Another way you might see that written is, we've used this notation, f prime of x. That's the first derivative, so it should be understood that f double prime of x would be the second derivative, and f triple prime of x would be the third derivative. Another way, if we were just thinking of y, we could say dy dx, d squared y over dx squared, and d cubed y over dx cubed for the third derivative. This is just notation, so try to keep up with that. I mean, how could f triple prime of x be the same thing as d to the third power? I mean, there's no mathematical operation involved here. We're just saying that's our notation for taking the third derivative. Let's go ahead and do some practice problems now. In this one it says if f of x equals 1 over x, find f triple prime of 2. So what you need to do there, or what I like to do, is just do these in order. Find f prime of x first, and we can think of 1 over x as x to the minus 1, so that would just be minus x to the minus 2. Then f double prime of x would be a positive 2, x to the minus 3. F triple prime of x, we're just taking the derivative of that second derivative now. That would be minus 6, x to the minus 4. Now when x equals 2, we need to think of that. F triple prime of 2, that would just be minus 6 over 2 to the 4th would be the best way to do that. That way we have a positive exponent. It's easier to simplify. Minus 6 over 16 is equal to minus 3/8. Let's think about this in terms of a physics application. Let's use this formula that we've talked about before. Y of time t is equal to y naught, an initial height basically, plus v naught t plus 1/2 a t squared. And remember, calculus was invented to study motion, so that's why I'm doing this here, just so you can kind of understand why we would ever want to take a second or a third derivative. Now let's take the first derivative of that function that I have there. That's that position function with respect to time. So we could say dy dt is equal to v naught plus a t. dy dt, think about that. Y, if that y was a distance, a change in distance over a change in time, that's what speed is, right? So taking the first derivative has given us the speed for this particular function. We can calculate the speed at any time t based on that original function. Now let's take the second derivative, d squared y over dt squared. If dy dt is a rate of change, that's what that gives us. The first derivative gives us the rate of change. D squared y over dt squared, the second derivative, gives us the change in the rate of change. And so that is going to just equal a. In this particular function, a stands for the acceleration. Now remember, when we've done this relationship before, y naught, v naught, and a, we assume those to be constant values. So in this position function, which is a commonly used function in physics, the acceleration is a constant value, and usually this is for the acceleration of gravity, and that's something we can assume that anywhere that you're standing on the earth, the acceleration of gravity is going to be a constant value. It's not fluctuating as you're standing at one certain position. First derivative gives you a rate of change. Second derivative gives you a change in the rate of change. That's what acceleration is, the change in velocity over time, the change in the rate of change. The third derivative would give you the change in the acceleration, or the change in the rate of change. Now, that sounds kind of weird, but that's really what it is. So by using calculus, we can, from one function, figure out velocities and accelerations at any point on that particular function. These are things that may have been very difficult to calculate without the use of calculus, and sometimes impossible to calculate. Okay, well that's all for lesson 38.